If you were to somehow eat the moon, the biological and mechanical results would be lethal. Applying the rigorous laws of physics and biochemistry to this absurd hypothetical reveals a sequence of failures that begin at the microscopic level. Earth soil is soft. It gets chemically weathered and rounded by water, wind, and atmospheric oxygen. Lunar regolith is formed in a hard vacuum by billions of years of continuous mechanical weathering, shattering rock into jagged, microscopic shards of glass. We know how dangerous this material is because we've already been exposed to it. During the Apollo 17 mission, astronaut Harrison Schmitt inhaled suspended airborne dust inside the lunar module. The resulting microabrasions in his lungs triggered acute lunar hay fever, causing severe throat soreness and a transient 20% loss of lung function. If you swallow that dust, the lungs are only the first point of failure. Looking at this data section on biochemical toxicity, we see the results of lunar regolith hitting human gastric acid. The free calcium oxide embedded in the dust reacts rapidly with water and hydrochloric acid in the stomach. This triggers a violent exothermic reaction, generating enough heat and concentrated alkaline agents to cause deep tissue necrosis and potentially fatal perforations. It gets worse at the cellular level. This clinical breakdown details oxidative stress via fenton chemistry. Lunar dust is packed with nanophase zero-valent iron. When this iron hits biological fluids, it generates massive volumes of hydroxyl radicals. These radicals tear through cellular structures, damaging mitochondrial membranes and actively mutating nuclear DNA. You can't filter these toxins out by using the dirt for agriculture either. Experiments attempting to grow plants in undiluted lunar simulant leachates show that high concentrations of heavy metal ions, like zinc, nickel, and chromium, completely choke out plant life and bioaccumulate in the surviving tissue. At a microscopic scale, the moon presents a highly reactive, abrasive hazard. It is a material that actively dismantles biological systems through a combination of physical microtrauma and toxic chemical cascades. So, what happens if we scale our thought experiment up? Let's bypass the toxic regolith entirely and replace the moon's entire rocky volume with actual cheddar cheese, keeping the total size exactly the same. Because cheese has an average density roughly 1/3 that of lunar silicate rock, the entire physics engine of the new body collapses. These equations show the result. The cheddar moon's mass represents only 34% of the actual moon, causing surface gravity to plummet. The escape velocity drops to a mere 0.029 meters per second. The kinetic energy generated by a simple human jump would permanently launch you out of the cheddar moon's gravitational pull and into the void. But the real violence happens beneath the surface. Planetary bodies are subject to immense central hydrostatic pressure, the force of gravity pulling millions of billions of tons of material inward toward the core. In our model, the center of the cheese moon reaches a crushing pressure of 558 megapascals. For context, the industrial high-pressure processing used to pasteurize food tops out around this exact limit, because beyond it, organic chemistry begins to break down. Cheese is highly compressible and stabilized by microscopic protein structures called casein micelles. Under 558 megapascals of pressure, those proteins cannot survive. The bonds holding the cheese together would disintegrate, forcing the network to dissociate into a highly compressed, dense, amorphous protein gel. As the giant sphere of cheese collapses inward upon itself, the friction of this compaction generates tremendous adiabatic heat. The core of our cheddar moon would become a massive, self-heating, semi-liquid ocean of pressurized, molten cheesewhey and lipids. Planetary thermodynamics make a food-based moon impossible. Gravity crushes the organic matter into a molten, self-heating core that destroys the body's integrity from the inside out. Which brings us to our final test. Let's say you succeed. The meal is over, and the entire mass of the moon is physically removed from Earth's orbit. The macroscopic consumption of our closest celestial neighbor triggers a total planetary collapse. The first casualty is global oceanography. The moon's gravitational pull is the primary driver of Earth's tides. Without it, the oceans are left relying entirely on the sun's gravity. Global tides would instantly shrink by roughly 66%. That reduction in water exchange kills the deep ocean conveyor belt, the thermohaline circulation. These currents are the planetary heating system responsible for moving solar thermal energy from the equator to the poles. Without tidal mixing to drive them, regional climates destabilize, creating unpredictable extreme weather anomalies worldwide. On the coastlines, the sharp drop in tidal range decimates intertidal ecosystems. Estuaries, salt marshes, and mangroves would dry up, triggering mass extinctions of specialized invertebrates and destroying the base of the marine food web. The loss of lunar light is just as devastating as the loss of gravity. Billions of coral polyps in the Great Barrier Reef rely on the precise light of the full moon to synchronize their mass spawning events. Plunged into dark, moonless nights, these populations would fail to reproduce, leading to the rapid collapse of reef structures worldwide. The ultimate consequence happens to the rotational physics of the Earth itself. The moon acts as a gyroscopic stabilizer for our planet. Its gravitational field dampens the pulling torque of the other planets, locking Earth's rotational tilt at a stable 23.5 degrees. Without the moon, Earth's obliquity would become highly chaotic, varying wildly from 0 to 80 degrees. If the planet tips on its side, the concept of seasons vanishes. Large portions of Earth's surface would be subjected to months of continuous, scorching daylight, followed by months of total, freezing darkness. The moon is the essential engine that stabilizes our climate, drives our oceans, and keeps this planet habitable. Its barren existence is what allows our world to remain alive.
Comment for next planet that you want to eat.